for the invitation. Okay, so maybe I repeat. Thank you very much for the invitation. I'm very happy to give this lecture. I'm not very used to give lectures to a broad audience, and so my lecture was thought more for scientists and mathematicians. But I will. So please do interrupt me with questions if you have any. So the topic I'm going to discuss today is billiards in polygons. So this is an example of dynamical systems, but let me just try to explain what is a billiard in a polygon. So we have a polygon, a planar polygon. It could be a rectangle, could be a triangle, and we have a point mass. You can think of the point mass also maybe which goes on a trajectory. So it moves inside the polygon, like in a pool, in a bar. But you can think of it as a light ray also, in the sense that the point mass doesn't have any dimension. It's really like a single point. It moves in straight line, and then when it hits the boundary, is reflected by usual reflection law. That means that the angle of incidence is equal to the angle of reflection, and it goes on like that essentially forever. And this will give some sort of motion, some sort of evolution. And the mathematicians and also maybe physicists are interested in what happens over a very, very long time. So what happens to this trajectory after, when the time essentially goes to infinity, it becomes very, very large. So notice in particular that here there is no gravity, there is no friction, there is you cannot put spin, there is no spin. Nothing like that. So it's a very abstract situation where we are only interested in this straight line motion and reflection. So I hope this gives an idea. So here is a discussion, a bit more precise discussion of what I just said. So a dynamical system simply means that we have a space. And in this space, we have something that moves, with time. So this is exactly the situation we have in the polygon. Now we have to distinguish in the polygon problem. So in the billiard polygon problem, we have to distinguish the configuration space and the phase space. This is notions that come from physics. So the configuration space is a space of positions on the table. So let's say we have a triangle. We mark the position of the point in the triangle. This is given by two coordinates. We are in the plane, and this is the configuration space coordinates. And then, since we are doing essentially Newtonian dynamics, we are looking at Newtonian motion. We want to also to record the velocity of the particle. So when we look at the motion, we don't look only at the position, we look at the position and the velocity together. So, and the position and velocity, so this is given by a couple of coordinates that here I noted by, so it's this, let's see if I can do this. This QV, so Q is the coordinate of the position that says where the point is in the domain, and V is the velocity, which is a vector in R2. So the velocity gives how fast and also in what direction the light ray is moving. So any questions so far? No? So far it's clear. So all right, so we have this point mass moving in a polygon and bouncing at the edges. With this law of here is angle of incidence equal angle of reflection. All right, now there is a principle from physics which is conservation of kinetic energy. So here it's a system that is conservative. There is no friction, no heat is developed, so all the energy is kept. And in this case, since there are no forces, there is no gravity again, so no forces, no external forces. This means that the kinetic energy, which is this quantity here, is preserved also by the reflection. The collisions at the boundary are called elastic, so there is no energy lost in the collisions. It's really bouncing without losing energy. So this means that the length of the velocity vector is fixed. So the kinetic energy is fixed. M is, say, the mass of the point. If it's a light ray, it wouldn't have any mass, but just similar. But if it's a point mass, it has some mass, but the mass is constant. So this means that the velocity is constant, and we can normalize it to be 1. What happens if we choose the velocity to be, the speed, actually, the norm of the velocity, to be 10? Well, it simply means that we're going along the same trajectory, bouncing around with a speed which is 10 times. So we go just faster, but over a long time, we see the same behavior. We just get to every point in the trajectory. We get there faster, but it won't change the features of this motion. So this is what I wrote here, that if we fix another value for the length of the velocity, which is the speed, nothing really changes. So this means that we can sort of reduce the phase space. We don't have to consider all velocity vectors. We can consider the configuration space. So this is the positions of the points. This is the circle of vectors of unit length. So we have a position, a velocity of unit length, so unit speed. And then we have to identify in some way the velocity vectors at the boundary, because there is an equivalence relation that expresses the fact that the incoming vector and the outgoing vector at the collision are essentially the same, are identified. So we have to identify vectors at the boundary to take into account the fact that we are following collisions. So we have a certain law of collisions. But anyway, so this is just you can think in some sense, you can just think that the system, the space of all possible states of the system is described by a pair where we have a coordinate in R2. So this is a pair of coordinates in the plane. And this is also a pair of coordinates, but the length of this pair of coordinates, so the sum of the squares, is equal to 1. So we have a position and a velocity of length 1. And that forms what is called a reduced phase space, where the motion takes place. So this is a picture. So this is, there are two examples of billiard. This is what is called a convex billiard, and this is a billiard in a polygon. So you see that this is, if you start here with this velocity vector, then you're going to go to the boundary and then be reflected with this low angle of incidence equal to angle of reflection. Then we continue along the trajectory gamma, which is a straight line. And again, you bounce, and then you continue like this. You would go here and so on. So this is the situation. And again, one is interested in particular to what happens over a long time. If you keep bouncing over and over, keep going forever, what is going to happen to this trajectory? Questions that I'm going to discuss are basically the following ones. So is it possible that the trajectory closes up and is called a periodic trajectory or periodic orbit? So the point starts, bounces again, and then after some bouncing, it comes back exactly where it started. So coming back to the starting point, and the starting vector will mean that if we keep going, the trajectory will just repeat itself on a loop. And this is the problem of periodic orbits. So it's one problem, finding them. And the other question is whether well, assuming that the trajectory doesn't go in a loop, will it go everywhere? So, with time, will it fill the whole space, like not only the whole domain, which is of course also a valid question, but will it fill all the domain and also all possible velocities? So will it go everywhere where it could go in the phase space, in the reduced phase space? So okay, so maybe I will come back to this later. There is another kind of billiards that I have. I don't have in the picture, which is the case where instead of bouncing inside the polygon, you can take a scatterer, so you can remove, say, a circular region from a domain, and then you cannot enter the region. So it's like, if you have sometimes if you are playing pool, you can put in your table some region that you cannot access, and then you imagine that your ball is going to bounce on this region. That adds some complication to this problem. So now I'm going to try to discuss some motivations, but before discussing motivations, let me just pause again and ask if you have any questions about this situation. So we are trying to study the motion of a point mass that in a domain, which will be a polygon, and which goes on a straight line and bounces at the edges with this precise law. You can think of a light ray in a mirror chamber, and this light ray goes on, and we are asking whether it can come back, form a periodic closed loop, or whether it can go everywhere and fill the space. So that's the main questions. But I will come back to these questions, discussing motivations. So there are motivations from physics, what is the relation between physics and a mathematical problem? Usually the point is that physics is more complicated, so the physical system will be more complicated. For instance, a physical billiard will have all sorts of complications like friction, spin effects, the fact that the mass is not a point mass, it will have maybe some radius, and so on. So mathematically, these problems are usually very complicated, and it's very hard to actually do rigorous deductive arguments on them and reach conclusions. So one thing that mathematicians do, and also physicists, mathematical physicists, is to simplify the problem and try to understand some features of the simplified problem, hoping that this will shed some light on the original problem. So billiards are among the simplest mechanical systems, it should be an S here, and provide some simplified models for statistical mechanics. So what is statistical mechanics? Well, very roughly summarizing this, there is a kinetic theory of gases that started with Swiss mathematician and physicist Daniel Bernoulli. The idea is that a gas is just made of a large number of molecules that bounce elastically against one another, and also maybe bounce against the boundary of the wall. So if you put a gas in a room like this one, you imagine that there are lots of molecules bouncing around and bouncing also with the boundaries. And with this idea, we try to derive macroscopic, properties like the temperature, the pressure, the heat capacity, whatever property that physicists are interested in, also for applications. We try to derive them as average quantities coming from this motion of a lot of particles. So you have very many particles that move around, and you try to derive laws describing macroscopic quantities like temperature or pressure as averages of certain observable quantities over the system given by all these particles. Now here I put a remark is that here I'm talking about n particle system, so there are many particles in some maybe three-dimensional space, like if you talk about gas in a room, it's a three-dimensional configuration space. To describe the position, we need three numbers, but there may be an enormous number, capital N, of particles, and but mathematicians have this way to always reduce, if they want, this to one particle. Well, how you do that? Well, you put the coordinates of all particles together in an enormous list of numbers that will give you coordinates in a much higher dimensional space. So an n particle system in a D space, like 3 space, is equivalent to a 1 particle system in a in a space which is multidimensional. So this is, by the way, this is one way to explain why we need a space with a lot of dimensions, because if you want to describe many particles, usually we do that by using multidimensional spaces. So of course, this is space. Since there are an enormous number of particles, the dimension of the space we need is enormous. So this is also, you see, an aspect of the simplification, that here we are studying one particle in dimension 2. So compared to the real problem, to the original physical problem, this is a little bit, almost silly, but we hope to be able to actually prove theorems on this very, very, very simplified situation. So, well, in statistical mechanics, there is an important idea that it goes back to Boltzmann, although I never understand exactly. I mean, I think the original formulation by Boltzmann is not so clear. It's been interpreted in many ways. There was a formulation later by Paul Ehrenfest that basically says that the trajectory, so the hypothesis that the trajectories of a multi-particle system run through all states compatible with the total energy of the system, which is exactly what I was saying earlier, is that the idea is that if you let these molecules go around, they will go everywhere they can go. What does it mean compatible with the total energy? It means that, of course, if the energy is conserved, the system cannot access states of different energy. So there is some constraint, essentially. But except for these constraints, the idea is that the particles are going to go everywhere. Not only they're going to go everywhere in space, but they are also going to go everywhere in velocities. So they are also changing their velocities in a way that they point in all possible directions for all of them. So it's just, they do whatever they can over time. And then there is the ergodicity. So this situation means that if you look at long-term time averages of some observation on the system, so you look at the system, you observe some aspect of the system, of this multi-particle system, then if you average over time this observation, after a long time, the average over time will be equal to the average over space. So this is an important principle. It's called ergodicity. That, well, it's an R missing here. Ergodicity. It's like here, ergodic. So it says that it's a consequence of the fact that a trajectory go everywhere. Not only they go everywhere, but they also distribute in the space in a way that they sample all possible states in kind of an equal way. And so we have a situation that if you average any observation over a long time, what you see is really the average over all possible states. And the system is ergodic if relevant observables. Well, this is also a tricky point, because usually I think in statistical mechanics we are interested in special observables, not just any observation of the system. But the notion of ergodicity is basically turns this into all possible observables. So a system is ergodic if observables, which means essentially parameters given by observation of the system, the long-term time average more or less is equal to the average of the observable over all possible regions. Over all possible states given by the assigned energy. So you have a bunch of particles that move. The particle move in some ways, or bounce around, etc. And then you have some kind of a measure that you're doing on the system. And of course, this measure is function of time. Since the particles are moving with time, the measure that you're making moves with time, changes with time. And the ergodicity says, well, if I take this series, it's called time series. If I take this series of observations, and I average over time, well, I will get essentially the same result as taking this measure over an arbitrary point, an arbitrary configuration of molecules, and just averaging over all possible configurations. So time averages equals space averages. This is the notion of ergodicity. I don't know if this is more or less understandable, but if you have questions, of course, please do ask. In more sort of simpler words, this is just same thing as saying that the molecules or the point mass, they go everywhere, and they go everywhere in some sort of a equally spread way. So they visit all regions of they can visit, and they spend in every region a time which is proportional to the volume of the region. So it's for small regions they spend less time, for large regions they spend larger time, and it doesn't depend on where the region is. The time they spend in the region only depends on the volume, on how big in terms of volume the region is. Okay, so this is some part of motivation from physics. So you see that this comes from the theory of gases, and from this idea that a gas is made of molecules, and the molecules bounce with one another, and et cetera, et cetera. And then we go down to a very simple mathematical model. There are also internal motivations that come in general from study of motion. Now, the study of motion didn't originate really. The mathematical study of motion didn't originate, as far as I understand, in statistical mechanics, but more in the motion of the planets. So the dynamical system, the first dynamical system, is the solar system. The planets move, go around their orbit, and we want to know how they evolve. So we want to know, for instance, what prevents the planets from crashing one into the other, or going crashing into the sun, or just escaping to infinity. We want to understand the long-term behavior of the solar system, say. Now, of course, we can address this problem, but we can also build up a theory that try to understand motion of systems in general. And if you build up this theory, that is the theory of dynamical systems that study motion of systems in general, there is a quote that from Anatol Katok, a prominent dynamicist of the 20th and 21st century, who died not long ago. That basically the idea is that you can test ideas or problems on billiard problems. So billiards are kind of a testing ground or playing ground for the mathematician interested in motion. So they display a variety of possible dynamical behavior, and you want to take it as a kind of a mathematical laboratory where you kind of experiment with ideas and conclusion. Now, to go a little bit deeper into this, the idea that proposed by Katok was that, well, not only by him, but also by him, is the fact that there are three kinds of dynamical behavior: the elliptic, the parabolic, and the hyperbolic. Now, this has to do with to what extent the system is chaotic. And to understand whether the system is chaotic, maybe you've heard about what is called the butterfly effect. So the important thing to understand is that if you have nearby initial points, well, you let them evolve, and their trajectory, their history as they move, they could stay closer together, so they can move together. And this will be essentially the elliptic behavior. So nearby trajectory do not diverge or diverge slowly. And this will be the case of billiards mostly billiards in convex regions. So this is the billiards in convex region is this case. So imagine that you take well, I should have put this into a picture, but imagine that you take a little beam around the trajectory, and then you let it bounce, and you know that a convex mirror like this will tend to focus the trajectories, right? If you think of a mirror, it's like Archimedes' mirror that they were used to destroy Roman ships. If you bounce against a convex mirror, the beam will tend to focus, and so the trajectory will tend to stay together for some long time. Then you may then have some defocusing, but let's not worry about that. So in this case, this is an elliptic situation where the trajectory tend to stay together. This one, well, when you bounce, this one is a little bit trickier, because when you bounce, indeed the trajectory stay parallel, right? If I'm close here and I bounce, my beam of parallel trajectories will still be a beam of parallel trajectories. So it seems to be also elliptic. And indeed, for a short time, it is. There is no divergence, the trajectories stay together. But here there is something that I haven't pointed out earlier that I'm pointing out now. There is an issue when we are near a corner. If a trajectory, so if the light ray or point mass moves and hits the corner, well, then we don't know what to do. And so in some sense, we take it that this trajectory is sort of dying there, is not going to go any farther. And you see that if you are on one side of the corner, like here, you bounce here, and then you go here, and then you go down here. If you're on the other side of the corner, you go a completely different path. So probably you know, if you play pool, that if you aim near a corner, well, if you hit on one side of the corner, you are going to do something, but if you hit on the other side of the corner, you're going to do something completely different. So this means that in this polygonal situation, there is some kind of splitting of trajectories, some kind of, they don't stay apart forever, but the splitting, the moment they diverge, is really given by whenever the beam gets sufficiently close to a corner. So that's the point here. And then there is a case when the boundary is well, concave, so it's like the other concavity, and then the beam is dispersed, and so you have divergence, and this is the case of hyperbolic. So there are these three classes, and there is a billiard. So the main point here is that there are three kinds of dynamical behavior that is related to how the trajectory behave, how nearby trajectory behave, whether they stay together, they diverge once in a while, or they diverge from each other exponentially fast. So this is the three cases. And the billiards provide a class of examples for the first case, a class of example for the second case, and a class of example for the third case. So it's useful to study billiards because we have all this, we can sample behaviors in very simple situation and try to understand what's going on in very simple situation. And in this lecture, we are going to focus on the parabolic case, which is billiards in polygon. So yeah, so a famous example of billiards is so-called Senai billiard that is dispersing is the one is not in my picture. So in that case, the boundary may have a convex piece, well, concave in a sense compared to the interior, and so it's the opposite. Is the opposite of this. In some sense, it's like you come from outside, and if you come from outside, you can check that the beams of parallel rays get spread. So, but yeah, that's not the topic here. So, well, maybe I will skip a little bit this in the sense that traditionally in dynamical systems, since it's more relevant for the solar system, the study has focused more on the regular motion, which is the elliptic, which is convex billiards, and random motion, which is the hyperbolic, strongly chaotic, sensitive dependence, butterfly effect kind of motion. And the intermediate behavior has been neglected, and is exactly intermediate behavior that I'm addressing in this lecture. That is, as you see, is much less understood. So hyperbolic is completely random, parabolic is intermediate, and the elliptic is, well, in the elliptic there are open problems. There is a famous Kolmogorov-Armin-Musa theory and so on, but this is not the focus of the lecture. So just to give an idea of the picture. Any questions? So for instance, if you study the solar system, you will be mostly here. So why the solar system stays together, more or less the mathematical explanation is that there is a, what is this? There is a certain stability in the elliptic case. There are lots of orbits that stay together for a very long time or forever. And this is a subject of Kolmogorov-Armin-Musa theory and also of the Khoroshev theory. So there are mathematical explanations why the solar system it's kind of stable. Okay. So now after this kind of introduction, I'm going to focus on billiards and polygons in particular. And I'm going to just to point out that there is a simple mechanical system that is equivalent to a billiard in a polygon. This is a well-known example that appears, for instance, in the work of Sinai and others. So it's a well-known example that relates a mechanical system to a billiard. So if you take 2-point masses, M1 and 2, on a rod, so the interval 0, 1 means really a segment, and you imagine a segment of length 1, a rod, and you imagine 2 masses. I mean, the rod is not really there. It's just the fact that the masses just move along a line. Well, in fact, they are constrained to be in between 0 and 1. And the 2 masses bounce against each other by elastic collisions, so without loss of energy. And they also bounce against the endpoints. So one way to think of this is like maybe sometimes this is the way I think it. You can have a tube. Everything is frictionless. There is no gravity and so on. You can have a tube, and inside the tube you have 2 balls exactly of the size of the tube. So they cannot pass each other. And then the tube is of length 1 is closed by 2 barriers, like 2. And then you let the ball, the 2 balls of mass M1 and M2 move in the tube. You give some initial velocities to them, and they will collide with each other elastically, and will also collide at the endpoints. So this is the idea is that this is some kind of a one-dimensional gas with 2 molecules, right? Instead of the room, we have a one-dimensional room, and instead of many molecules, you have 2 molecules of masses M1 and M2. So you see, this is really a caricature of what's going on in some sense. But well, you can ask, what about this? What is going on if I take 2 molecules and I put them in a room which is one-dimensional? And well, first you do an exercise that actually, I know I should not put formulas, but I have the exercise or part of it in the next slide. So the exercise says that this problem, 2 molecules in a rod of, in a one-dimensional room, is equivalent to one point mass in a triangle. So it's a billiard problem, but now it's 1 point in a triangle, in a right triangle to be precise, and the angle, one of the angles of the right triangle is given by the arctangent, so the inverse tangent of the square root of the ratio of the masses. So you can go from this molecule problem, 2 molecules in 1 dimension, to 1 point moving inside a right triangle with a certain angle. And you see that the angle really depends on the masses that you have to start with. And if you do this, you can do this with 3 masses on a circle. So now your room is doesn't have a boundary, it's like circular. And you get a similar situation, but now the polygon is an acute triangle here, acute triangle, and the angles are given by these formulas. This is more complicated exercise, but with same flavor. So there is a way to go from certain simple mechanical system where you have some caricature of a room with molecules to billiards in certain polygons. So, well, here is the exercise only for the first case. So, well, I will maybe essentially skip it. The idea is that you have to write the kinetic energy, and then you want to do a change of variable to reduce the kinetic energy to the usual Euclidean form. That's the essential step. So this is the change of variable, and the original constraint, it says that where is it? The original constraint, it says that the position x1 of the first mass is smaller, always smaller than the position x2 of the second mass, and both are between 0 and 1. So x1 is the position of the first mass, x2 is the position of the second mass in this one-dimensional room. And after change of variable, you rewrite this constraint in this way, and you see that this represents a right triangle with one angle being given by this formula. So that's more or less the exercise. So this is, if you do some physics or some mathematics, then you know this how to do this kind of exercises. But it's not very complicated. It's just essentially you have to know what these quantities are and then do some change of variable. Okay, so any questions? So summarizing, now we just motivated in several ways why we want to study this motion of one point in a polygon. And now I mentioned already that there are two problems that we're going to look at. One problem is the problem of periodic orbit. So do we have a way of starting a trajectory in a motion of, say, the light ray or the point mass in the polygon that after some number of bouncing exactly comes back to the initial point with the initial velocity, so that the trajectory traces itself over and over. That's the periodic orbit. And the ergodic properties are related to the idea that most trajectory will go everywhere. Of course, not all of them, because they may be periodic ones, but most trajectory will go everywhere, and they will go everywhere in a way that essentially they distribute everywhere equally. So this is this periodic orbit question is in fact very hard, and the answer is not known. So we don't know whether all polygons have a periodic orbit. So now let me try to explain what we know. And so the question is exactly this: do all billiards in polygons have a periodic orbit? So there is an answer, yes, for acute triangles. And the answer yes goes back to the 18th century when Fanianis solved some kind of question that is formulated in a different way, but it turns out to be equivalent to saying that the acute triangle has a periodic orbit, in fact, a beam of periodic orbits. So the Fanianis problem is the following: for a given acute triangle, determine the inscribed triangle of minimal perimeter. So you can imagine to do this. You take a triangle made of maybe iron bars or something like this, and then you take some rubber band, some length, or that you can make tighter, and you try to put it around the triangle in a way that it wraps around, going around the edges. And then if the band is tight enough, it will go to the inscribed triangle minimal perimeter. And the answer is not very hard, and Fanianis found it by some kind of a calculus ideas. And the solution is the so-called Orphic triangle. So in other terms, if you have a triangle, if you take the foot of the heights of the triangle, you take the 3 foots of the 3 heights, and you join them, you will find the described triangle of minimal perimeter. So that's the solution. Well, there is also another principle that says, if you look at some closed curve made of segments that join the edges, it is an orbit of the billiard problem if its length is a critical point, means the derivative is 0, so a minimum or a maximum of the perimeter. So this problem gives a periodic orbit because it minimizes the perimeter among all possible triangles. So the fact of being minimal implies that if it is also a periodic orbit of the billiard problem. But one can also see geometrically that it respects the idea that angle of incidence is equal to angle of reflection. In fact, there is a one-parameter family of periodic orbits which have period twice the length of the Fanianis triangle, and they travel parallel to it. I think I have a picture of this. So this is the Fanianis beam. In other terms, in the middle, there is the orthic triangle. H1, H2, H3 are the foot of the heights. So here's the heights from B, is the heights from C goes there, and the heights from A goes to H1. And you have this triangle. But then what if you start not on the Fanianis triangle, but just a little bit off, but you go parallel? Well, you can see that you go close to it, you go parallel to it, but you don't close at the first time you go around. You need a second time going around before you close. So all trajectory which are not on the Fanianis triangle but are kind of go parallel to it will have double length, but they do close. They are periodic. So this is an example of periodic orbits. What I mean by a periodic orbit. Now, one question is there another one? Is there any other one? And this question is open, so nobody knows if an acute triangle has another thing like this. I mean, of course, I'm not limiting to 3 bounces. Any number of bounces will be allowed. So this is not known, and that's an open problem. Do all acute triangles have another periodic orbit, which is not part of Fanianis beam? And well, then there is a question: what about triangles that are not acute, near right and isosceles triangles? There are results for near right and isosceles. I quoted some results, but the results sometimes are kind of elementary. Sometimes you have to fight harder to, the mathematical theory becomes more complicated. But you see, these results are mostly rather recent. So, compared to the 18th century, here we are in the 90s. This result is 2009. But okay, we can still deal with this, and with near right. Near right means almost right triangle with an angle which is near 190 degrees, or they are near isosceles. So they're almost, we have 2 angles that are very, very close to be equal. But there is the problem of obtuse triangles. So an obtuse triangle is one angle is very large, right? Is larger than 90 degrees. And of course, we exclude the other cases. So obtuse means also here means not near 90 degrees. It means like sort of larger. Well, there is a proof by Rich Schwartz in 2009 that periodic orbits exist for angles up to 100 degrees. And recently, the record has been improved by these people to 112.5 degrees. So this means, if you ask whether we know that an obtuse triangle has a periodic orbit, the answer is yes by these people if the large angle is up to 112.5 degrees. Now, of course, what about the other angles? Well, the answer is that we don't know. And these proofs are based on, I will explain a little bit more, but they're based on computer-assisted search. You know, you can run these orbits, these bouncing orbits on a computer and try to find, the computer will find candidates to be periodic orbits. And then once you know the candidates, you try to prove that indeed, I mean, the mathematician wants proof. The computer is not enough. There's also a problem that as you get close to 180 degrees, right? The largest possible angle for an obtuse triangle is going to be close to 180. The computational complexity of the problem goes up enormously. And so most of the improvement between 100 degrees and 112.5 degrees was just using more powerful computers, essentially. So if you use even more powerful computers, you can go maybe a little bit farther, but there is no way that you can, this method is going to get you to 180 because the complexity just becomes, I mean, maybe, I don't know, maybe in some millennia, I don't know. But anyway, so the complexity really increases enormously. So a remark, why don't we do what we were doing for the acute triangle, right? Just trying to find the shortest inscribed triangle. Well, the problem is that the shortest inscribed triangle is degenerate, it's just a segment, right? So if you put your 3 points on the edges and you try to minimize the total length, the perimeter, then you will find just a segment that joins the obtuse vertex with the opposed edge. And so this is not an inscribed triangle, and it won't give an orbit because it goes through the vertex. So it's not good. So you can't use this argument, the Fanianis argument for this. Questions? Yes.
One are close to this limiting path which get
No, in general they are complicated. I will, yes, they're very far, yes, and you need many bounces. Sometimes you need an increasing number of bounces to get a periodic orbit. I will say something more in a moment. Yeah, I mean, you can't limit yourself to bouncing 3 times if you hope to find or whether they are close to.
Are they getting close to this limiting path?
That I'm not. Well, I mean, since they are long, they will sort of go a little bit everywhere. So yeah, yeah. I don't think they are going to especially close to the limiting path. Yeah. So since the method proof is geometric, I thought I would try to give you a flavor of what's going on. So one idea is what is called unfolding. Now, there will be a feature about unfolding, but unfolding simply means that where we're trajectory bouncing at an edge, instead of following the trajectory that has bounced, so the light ray comes and bounces, what we're going to do, we're going to reflect the polygon, like a mirror reflection of the polygon, and we're going to follow the trajectory as a straight line through the wall and look at it in the copy of the table. So this, by the way, I found that comes from, I mean, it was discovered later, but there is a proof of the Fanianis Theorem by Schwarz that is at the end of the 19th century, which is geometric like this. So maybe this is a bit small, but you see here you have the ABC is the original triangle, and then it's reflected on this edge. And here is here, so this is new A, and then it's reflected again, and then it's reflected on this edge here, and it goes down here, and then it's reflected once more, etc. So you look at a series of reflections following following, well, this is the orthic triangle, the one you're trying to show that it minimizes the length. And this is another triangle, right? Another inscribed triangle. So the proof consists in showing that the length of this orthic triangle is shorter than the length of this other triangle, which is kind of a random triangle that you drawn there. And the point is that as you do these reflections, you can see the length of the orthic triangle. Well, the legs of the edges of the orthic triangle, they form a straight line. The straight line joins, say, this point to this point, while the edges of the other triangle, after reflection, they form some kind of a zigzag line. Well, it's hard to follow, but you can see that. Well, for instance, you have this edge here, and then I guess you have this, maybe this one here, or this one, no, this one. So anyway, so it doesn't go in a straight line, and so clearly it has to be longer because you go between two parallel lines, and the orthic triangle produces a straight line, and the other triangle produces some zigzag line that goes from here to there. So the orthic triangle produces a shorter total length. So, but from the Billiard point of view, you can also say that this clearly is a trajectory of the billiard, right? So it's if you reflect the triangle, the trajectory of the billiard, you see it as a straight line. And so indeed, if you try to find periodic orbits, you do reflections, and you're trying to find beams of straight line that go from one parallel edge to another parallel edge, like here. So that's essentially the main idea. So that the important point is that instead of to find trajectories, instead of trying to follow the trajectory as it bounces around in the triangle, you want to reflect in some way according to some combinatorics, some choice of the sequence of edges that you're using to reflect, and then you try to find straight lines that don't meet singularities, and that go from one copy of an edge to another copy of the same edge, which are parallel, that end up to be parallel, like in this picture. So that's the idea of the unfolding, and it gives some geometric proof of Fanianis Theorem. Originally it was like a calculus, but here it's like, just really a picture. So then, in order to understand periodic orbits, one do something that is called coding. So how do we code a periodic orbit? Well, we just give the coding is just like this. We give a number to every edge. So this is the edge number 1, this is the edge number 2, this is the edge number 3. And then as we follow the orbit, we record the label of the edge. So this is a periodic trajectory with code 1, 3, 2, 1, etc., etc. I think it's coded starting from this point here, right? So 1, 3, 2, 1, 2, 1, 2, 1, 3, etc. So that's the way we want to understand the periodic trajectories. For instance, the Faniani orbit has code 1, 2, 3, but the orbit being the periodic orbits which are nearby, they go around twice, so their code would be 1, 2, 3, 1, 2, 3. And then the proof goes like this. We do a computer search that finds words of periodic orbits. So we try to find the periodic orbits by running some computer program that finds periodic orbits and also the code of periodic orbits. Then there is an important notion, there are stable words and unstable words. So what is a stable word? I mean, if you have an orbit with a certain word, it could be that as you move your triangle a little bit, you just change a little bit the angles. It could be that this trajectory, this periodic trajectory persists, so then the word is called stable. It turns out that it may depend just on the word. For instance, odd words are always stable, so the periodic orbit always persists when you move the triangle. And there are unstable words, so words that maybe you have a periodic orbit for this triangle, but as soon as you move the triangle a little bit, no more. So of course you want to find stable words, and once you have stable words, you know that you can find some little region in the space of triangles where you have periodic orbit, and then you have to find sufficiently many regions to cover more and more possible angles. So that's the game. So basically, computer suggests codes. There is a lemma that says certain codes are stable, and then certain words are stable. And then stable words will give you a little patch in the space of triangles where you know that there is a periodic orbit. And then you have to find sufficiently many codes to actually cover the space of triangles. The space of triangles is parameterized by two angles, right? I mean, the sum is 180 degrees, so you have two free parameters, so some domain in the plane. You try to cover as much as possible with patches that corresponds to stable words, and so you know that there are periodic orbits there. So that's roughly the idea of how it works. Questions? Okay, so maybe this is people really started a search for, I don't know if I put it somewhere, but maybe later. People started a search for periodic orbit. Maybe I put it earlier here. Yeah, there's a website, the Great Periodic Path Hunt, that essentially means that people are trying to find codes by computer and trying to improve this 112.5 degrees. But as I said, I mean, they can beat the record, but they can probably not go all the way to actually showing that every triangle has a periodic orbit by these methods. So how much time do I have? Not much, right? Huh? I'm almost over. Okay. Well, I wanted to say something about ergodic properties. So probably there won't be much time to talk about ergodic properties, but let me just say that this Billiards in polygon have zero entropy, so the entropy measure essentially how much they resemble a coin toss. So they do not resemble a coin toss. This was proved by Katok again. And then there are some results about ergodicity. Basically, the results are about existence. We know that there exists some ergodic polygon. I mean, in fact, we know that the ergodic polygons are dense. This was proven in the 80s by these three people. And the question whether almost all are ergodic is open. We know that they are not all ergodic. So on the other hand, I wanted to comment, what does it mean almost all? It means that if we choose the angles at random, just without, in some kind of a random way, without any specification, well, we will expect the polygon to produce an ergodic billiard, but this is open, we don't know. Now, again, the physicists do numerical simulations, and mathematical physicists, they provide some hints because in just numerical simulations. And from these numerical simulations, we suspect, we know, depending on your community, that if you take an acute triangle with irrational independent angles, so the angles are kind of, in some sense, random, except for the fact that their sum is 180 degrees, then they are ergodic. They even have a stronger ergodic property, which is called mixing. This was done by these two people, Casati and Prosely, in 2008. And but right triangles, remember that our 2-point masses in a rod was giving a right triangle. The right triangles may fail to be ergodic, again by numerical analysis in 2013. But the problem is subtle because if the angles are very well approximable by rationals, then they look like they are ergodic. This is a more recent numerical simulation by these people here. So we should expect that most are ergodic, but maybe sometimes they are not ergodic. And the fact that they are not ergodic may be related to the fact that there is a right angle. So the right angle in some sense is special. So of course, if you don't have it on most triangles. So yeah, so just to say something more, in fact, there is, if you look at Billiards in Polygon, there is a basic dichotomy between the rational case and a non-rational case. So the rational case, in the rational case, you look at the group generated by reflection with respect to edges. So if this group is finite, then we have that the phase space is followed by invariant surfaces. So, like for instance, if the table is a rectangle, right, then you have a reflection with respect to an horizontal line and reflection with respect to a vertical line. So the group generated will be a group with 4 elements. It's finite. And if you have this, the Billiard flow is not ergodic. And this is more or less the same as saying that the angles of the polygon are rational multiples of 2 pi. And so in this case, there are invariant surfaces. So if you start, more or less, this means the following: if you start with at a certain angle, then you keep track of what angle you started with. So the angle is not always the same because, of course, you bounce, so there are some reflections. But essentially, the invariant surface is a way to say that the motion happens on a 2-dimensional object, which is basically determined by the initial angle. So in this case, in this case, clearly, you do not have ergodicity because you cannot go everywhere. You're basically stuck with the initial angle. Now, this case is much better understood. It's very special because you have this rational constraint, but it's much better understood. And most results on polygons which are non-rational are obtained by starting with a rational case. So the case when the angles are multiples 2 pi times the rational, and then using some approximation. So this is really the theory that is well developed for this special case. And from this special case, people try to deduce consequences for the general case. In particular, this theorem here that there are some ergodic polygons in any number of edges is obtained by approximation. Well, it's an approximation result, so it's not written here, but it's obtained by approximation with this rational case. And well, there are many things I wanted to tell you, but you see, I can skip all this and maybe answer questions. So so this theory of rational polygons, they are based on a lot of developments in the study of surfaces, because the motion happens on the surface. And so there's been a lot of developments in what is called the tachymular dynamics or tachymular theory, which is the study of surfaces in the past 40 years. So here there are some names. A lot of people, including Fitzmaurice, have contributed to it. And then, this theory understands very well, or rather well, the rational case. But the general case is still not very understood. And some results we obtain, as I said, by approximation. So I guess that this is my summary. So Billiards in general polygons are not well understood. And these are some open questions. Does every polygon have at least one periodic orbit? Do acute triangle have a non-Faniano periodic orbit? This I mentioned. Does every non-rational polygonal billiard have a dense orbit? You can ask whether you have an orbit that goes everywhere, just one. And there is a question about whether the random polygon is ergodic or more. And well, this mixing probably I haven't had time to talk about. These problems are very hard. They were included in a list of 5 most resistant problems in dynamics, and nobody has any idea in the mathematical community really about what to do about them. There are no methods, no tools, nothing. The only thing we can do is to essentially study the rational case and then do some approximation. And here's what I wrote here: was billiards in rational polygons are rather well understood thanks to great developments in this theory of surfaces. It is called Teichmüller dynamics, and some ideas that are usually labeled as renormalization. So, okay, so I'll stop here and thank you for your attention.
Thank you very much, everyone, for your efforts to make